All right, pre-AP chemistry. This is your additional assignment. I'm going to be going ahead and showing you how to calculate formal charges. Okay. Hopefully this video doesn't take too long. And just a reminder, remember this assignment, I'm not going to be going over in class. Okay. You have to rely on this video to complete this assignment. Now, obviously, if you have a question on this assignment, you're more than welcome to bring it up during class. I'm just not going to give the lesson on this during class. Okay. Again, you need to rely on this video. Okay. So with that being said, you have a note section and a practice section. I'm going to go ahead and go over the note section. All right. And then based on what I show you guys here, hopefully that will be enough for you all to complete the practice session. Okay. And again, this is due on Friday. All right. So let's go ahead and get started. Open this up on Cami. Okay. So what is formal charge? Come on, Cami. What is formal charge? Okay, so formal charge is the number of valence electron in an isolated atom minus the number of electrons assigned to the atom in the Lewis structure. Okay, so in other words, the number of valence electrons assigned to an isolated atom. Okay, what it means by isolated atom is that if you just take oxygen, right, you have 6 valence electrons, right? So formal charge is the number of valence electrons, in this case, it's 6, minus the number of electrons assigned to the atom in the Lewis structure, okay? So if you're looking at oxygen in the Lewis structure, let's say you have water here, you're going to go ahead and subtract the electrons that oxygen has according to that molecule. Okay, so it just depends on what you have. Okay, so let me go over these points down here, and then I'll go ahead and go over that actual example down here. Okay, so to calculate formal charge on any atom in a Lewis structure, we assign electrons to the atom as follows. Okay, so this is where I was showing you that X here, right? We figure out X from these 2 points right here. Okay, so 1, all unshared or non-bonding electrons are assigned to the atom on which they're found. For any bond, be it single, double, or triple, half of the bonding electrons are assigned to each atom in that bond. Okay, so let's just go ahead and do this example. Okay, so here's what you guys are going to do. Okay, the actual assignment it's going to look just like this. Okay, you're going to be given your target molecule. In this case, it's water. All right, you have to go ahead and write. I think actually I write down the atoms that are in the molecule already. Yeah. So in this molecule, we have hydrogen and oxygen. Okay, the total number of valence electrons. Okay, for hydrogen, we know that it has 1 valence electron, right? But there's 2 hydrogen atoms. So we're going to go ahead and multiply that by 2. That gives us 2. Oxygen just has 6. Now we're going to total them. Okay, the total number of valence electrons in this molecule is then going to be 8. Okay, and then here we have to go ahead and write down what the central atom in the molecule is. Okay, so for that, remember we just went over this. Okay, it's this first point right here. Okay, determining the central atom in the molecule. Okay, if there's only 1 atom of an element, it is more than likely the central atom. Okay, plus we're not going to use point B right now, but if we look down at point C, it says hydrogen will never be the central atom. Well, we have H2O, right? We know that hydrogen can't be the central atom. So by default, we know oxygen is going to be our central atom. Okay, so we've figured out the basics here. All right. Now let's go ahead and make the molecule. Okay, remember AVBN. Now, guys, I'm going to go over this relatively quickly, okay? By the time you get to this assignment, you should be able to figure this out relatively fast, okay? So A, remember that stands for the number of spaces available on the atom. Okay, so if we take hydrogen, it can fit up to 2 electrons. If we take oxygen, it can fit up to a total of 8 electrons, right? 8 and 2. We have 2 hydrogens, right? So really we have 4 from hydrogen. So in total, we can fit up to 12 electrons. There are 12 available spaces. The number of valence electrons, okay? There are, well, we have that number right here. We have 8, okay? The number of electrons that'll be used for bonding, that is just A minus V, which is 12 minus 8. That gives us 4, all right? So these are our bonding electrons. The number of non-bonding electrons, that's going to be V minus B, which is 8 minus 4. That also gives us 4. All right. Central atom is going to be oxygen. Okay. We're going to use 4 electrons for bonding. So let's go ahead and add our hydrogens. 2 electrons there, 2 electrons there for a total of 4. That leaves us with 4 non-bonding electrons. Hydrogen has a full shell. This hydrogen also has a full shell. That means we have to go ahead and give this guy the remaining electrons. Okay, so now oxygen has 2, 4, 6, 8 electrons in total. He has a full shell. He's happy, right? Okay, so now we're going to go ahead and calculate the formal charges of these atoms. Okay, and again, that helps us determine if we're dealing with a molecule, say like NH4, if we're dealing with a charge, that's going to help us figure out where the charge on the molecule lies. Okay. Obviously, there is no charge on water, but it'll still serve as a good example for using this formula. Okay. So here is your formula, pre-AP, right here. Okay. So it's the number of valence electrons. Let me just go ahead and write this out. Let's just go ahead and do that. All right, so formal charge. Let's go ahead and do this right here. Okay, so we know that this is our molecule. Let's go ahead and find the formal charge of oxygen. I'm going to write FC for formal charge, and in parentheses, I'm going to put O for oxygen. Formal charge equals our number of valence electrons. For oxygen, this is going to be 6. So I'm going to write 6. Ay, 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 this freaking pen. Sorry, guys. Oh, my God. Let's try that again. Okay. So our number of valence electrons is going to be 6. All right. And then it's going to be half the bonding electrons. Okay. Well, how many electrons are bonding to oxygen right now? We have these 2 and these 2, right? So oxygen has 4 electrons bonding to it. Well, we're going to take half the bonding electrons, right? So we're going to take, I'm going to write this, times 4. Okay. Just go ahead and erase these 2's. And then we're going to subtract from that the number of non-bonding electrons, okay, which would be 2, 4. All right. So now we have 6 minus half of 4, which is going to be 2, minus 4. That gives us 0. So there is no charge on oxygen. Okay, the formal charge of oxygen is 0. Okay. Let's do the same thing for hydrogen. I'm going to try to squeeze it in here. All right, so there's oxygen. Now for hydrogen, okay, the number of valence electrons is going to be 1. Okay, just 1. And the number of bonding electrons is 2. right? There's 2 electrons on this hydrogen. There's also 2 going to this one. So each one has 2. We're going to take half that number. And then we're going to go ahead and take away the number of non-bonding electrons. Well, hydrogen doesn't have any non-bonding electrons, so it's just 0. So that leaves us with 1 minus half of 2 is 1. That leaves us with 0 as well. Okay, sorry guys, I know this isn't the neatest writing. Okay, well this is good. This is what we want. There's no charge on water, right? We don't have a plus charge here or a minus charge of anything. And our formal charges show that. They add up to 0. We're good, okay? So there's your first taste of formal charge, okay? It's kind of pointless, not pointless, but it doesn't really do us too much good to use formal charge on a compound that doesn't have a charge like water. But again, this is your first experience with formal charge. This is going to get really handy for when we're working on polyatomic ions, which we happen to have right here. Okay, so what is a polyatomic ion? Okay, now I know for 7th period, I didn't get a chance to cover this in class. Okay, I will go ahead and cover what polyatomic ions are on Thursday. Okay, but just a quick little understanding, polyatomic ions are basically, well, it's in the name, right? Poly means many, okay? Atomic, well, we have atoms, right? And then we have ions. So basically what this means is that we're working with ions made of many atoms. Okay, simple enough, right? Poly, many, atomic, atoms, ions, ions. This translates to ions made of many atoms, which is what we have right here, okay? We're used to showing like, magnesium 2 plus or Cl1 minus. We're used to seeing single atoms carry charges, right? When we were working with ionic compounds, that's what we would see. But remember when we made that Venn diagram, right? Remember when we made that Venn diagram, I wrote over here when we were talking about ionic compounds that, most ionic compounds are made from metals and nonmetals, right? But that's not always the case. Okay, that's not always the case. And that's where polyatomic ions come in. Okay, we can have some ionic compounds that don't have any metals. All right. But that's not the focus of this right now. The focus of this is basically finding the formal charge. So let's go ahead and do that. Okay, so for polyatomic ions, the charge found on the ion often results from one or more atoms having a formal charge greater than or less than 0. Okay, and we'll make sense of that once we get started on this. So we're going to do the same thing. Nitrogen. Okay, nitrogen has 5 valence electrons. Hydrogen has 1, but we have 4 hydrogen atoms. So really, we have a total of 4 valence electrons from our hydrogen. Now, this next part is important. Okay, so if you've been zoning out, please zone back in. The total number of valence electrons, we have 5 plus 4. That gives us 9. We are going to subtract 1. Okay, why? Because we have a charge here. Let me go ahead and get rid of that circle. Guys, we have a charge here. Okay, anytime you have a charge, if it's positive, you're going to subtract electrons from the total number. If it's negative, you are going to add electrons to the total number. In this case, we have a positive charge, and it's a positive charge of 1. So we have 1 less electron. So really, we have a total of 8 valence electrons. Okay? Please be aware of that. Okay, central atom in the molecule. Remember, okay, to determine the central atom, if there's only one atom of an element, it's more than likely the central atom. If you're working with hydrogen in another atom, hydrogen's not going to be the central atom, right? In this case, there's only one nitrogen, so we know it's going to be nitrogen, but we also know that because hydrogen will never be the central atom. So nitrogen is our central atom. Okay, now we're going to go ahead and build the compound, AVBN. I'm going to go through this real fast. Total number of spaces that can fit on nitrogen is 8. Each hydrogen can fit 2. We have 4 hydrogens. 2 times 4 is 8 plus 8. That gives us 16 spaces. Number of valence electrons, 8. Okay, 8, not 9, 8. Our total number of bonding electrons, that's going to be 16 minus 8 for 8. We have 8 bonding electrons. Swear to God. If you're religious, excuse my foul tongue. Non-bonding electrons, okay, it's going to be V minus B. So we have 8 minus 8. That gives us 0 non-bonding electrons. This is valence electrons. Okay. All right. So let's go ahead and build our molecule. Okay. We know nitrogen is going to be our central atom. So here's nitrogen, right? We have 8 bonding electrons. 1, or 2, 4, 6, 8. Hydrogen, 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 hydrogen. All right. So we know that this molecule has a positive charge, right? This polyatomic ion carries with it a charge. So the way we actually show this, guys, we're going to put this molecule in parentheses and put this positive charge outside, okay? So this whole molecule carries a positive charge, okay? Now that's all fine and dandy, but what we're interested in is the formal charge. All right, so the formal charge is going to tell us where on this compound is that positive charge coming from, okay? So let's go ahead and do this. Let's go ahead and do the formal charge for nitrogen. FC for formal charge. We're going to write nitrogen in parentheses. Okay, so what is the formula? Formula is write the number of valence electrons. In this case, nitrogen has 5. So we're going to write 5 minus half the bonding electrons. In this case, nitrogen has 2, 4, 6, 8 bonding electrons minus the number of non-bonding electrons. Nitrogen doesn't have any, so it's 0. All right, write this out again. 5 minus 4, that gives us 1. Right, that gives us 1. Okay, let's do the same thing for hydrogen. Now, something I want to point out, each of these hydrogens are basically the same, okay, meaning they're all bonded to the same element. So we only have to do formal charge. Once we figure out the formal charge for one, we can apply that formal charge to all of them, okay? And here's what I mean. The number of valence electrons on hydrogen is 1. The number of bonding electrons is going to be 2, right? Each of these hydrogens has 2 bonding electrons. We're going to take half that number. And the number of non-bonding electrons on hydrogen is 0. That leaves us with 1 minus 1. That leaves us with 0. Okay, so each of these hydrogens is basically neutral. There is no charge. Okay, now on the other hand, hydrogen or nitrogen has a positive charge. Okay, he carries a positive 1 charge. So the reason why this molecule is positive is simply because the nitrogen has a formal charge of positive 1. Okay, he is the culprit. He is the reason why this molecule is carrying a positive charge. Okay. Why is this important? Why do we care? Okay. Because moving forward, we're going to be working with more complex molecules. Okay. Remember, I said that we might see some ionic compounds that work with polyatomic ions. Okay. So it's not going to be the simple NgCl2 all the time. Okay. It could end up being something along the lines of NH4 2O. Okay. So that's why we're going over this. You guys need to understand where the charge is coming from, okay, where it's located, and why. All right. So I hope these notes were succinct enough to make sense of formal charge. Let's go ahead and take a look at the main assignment. Okay, let me go ahead and pull up the main assignment. Formal charge practice. Go ahead and open this up with Cami. Okay. All right, so here you go. You have a total of 5 problems, okay? Now, there may not be enough room for some of you guys. Really, I mean, if you don't have a drawing pad, it's a pain in the butt to do this sort of thing online, okay? So you guys are more than welcome to do this. In fact, I encourage you to do this on a separate sheet of paper, okay? Because you might have a lot of mistakes that you're going to have to erase. And, you know, doing it online like this, again, if you don't have a drawing pad, it's a pain in the butt. But here's what you're going to do. You're going to go ahead and do the same thing here, okay? You have these 5 molecules, all right? Some of them carry a charge. Some of them don't, okay? You have to make sure that your formal charge adds up to whatever charge is on the molecule, okay? So like we did back here, the formal charges add up to 0. That's what you want. Oxygen doesn't carry a charge. Down here, the formal charges add up to 1, right? If I take this positive 1 and this 0, you guys know this, right? 1 plus 0, obviously that's 1, right? So the formal charges should add up to the charge on the molecule, okay? So when you get to BrO3 minus, when you get to CO3 2 minus, your formal charges, they need to add up to the charge that's on that molecule, okay? If they don't, something's wrong, all right? So just keep that in mind. This is your assignment. This is due on Friday. Again, if you have any questions, please do not hesitate to ask. All right. And that's it. That's the video, guys. Take care.